Hi class, this is the batch review for our examination long test number 2, and these are again the reminders for the examination. So do take note that you will be answering your putting your answers on the answer sheet, so don't write your answers on the questionnaire. Secondly, these are the type questions that we have. We have MCQ or multiple choice question. Do take note to write the capital letters only of the correct answer, not the small letters. You also have true or false, wherein you're going to write the word true or the word false. Do not write T or F, but write the whole word. And then you will have short essays for about 2 to 4 sentences only. Other reminders for the exam is that you would be writing on or marking. You can write on or mark the questionnaire. If you need to make any kind of markings, it's all right with me. Number 4, you can make erasures if you don't have correction tape. So make sure that you will cross them out, the wrong answers, and then you make it very, very clear what are your correct answers. Number 5, 6, and 7, just bring extra pen, no pencil please this time. Go to the CR or get water before the exam starts, and of course put all your things on the walls of the classroom. So those are just the important reminders. Now in terms of the details of our exam, there will be 40 items. It will be for 60 minutes, and as mentioned a while ago, multiple choice question, true or false, or short essay. Now for that breakdown of the question, there will be 7 questions coming from the light independent reactions, 6 questions from the alternative carbon fixation pathways, 7 questions from the overview of cellular respiration, 7 questions from glycolysis, Krebs cycle, and oxidative phosphorylation, 6 questions from the anaerobic respiration, and 7 questions coming from comparison of photosynthesis and cellular respiration. Now, starting with our discussion today, take note that we have already done with the light reaction. So what happens here is that light is absorbed, water is split into oxygen, of course hydrogen is produced, and then two important things that are very important for the next topic, which is production of ATP and the NADPH, which would be used for Calvin cycle. Now in the Calvin cycle, the most important thing here is that the ATP and NADPH will be used to fix carbon dioxide, later on becoming what we call as glucose or what we call as sugar. Now do take note that the Calvin cycle is happening inside of the stroma, which is the fluid filled space inside of the chloroplast. So this is where our examination will be starting, and that will be the Calvin cycle. So let's go into the details of the Calvin cycle. Now first of all, do take note that there are 3 stages of the Calvin cycle. The first one is carbon fixation, reduction, and regeneration of RUBP. So these are the 3 stages of Calvin cycle. So again, CRR, carbon fixation, reduction, and regeneration. So let's talk about these stages. Starting off with the first stage or first phase, which is carbon fixation. Now, there are a number of names that you have to really take note of. RUBP, carbon dioxide, Rubisco, and 3-phosphoglycerate. Also take note of the number of molecules of each, which are very important. Now, what happens is that the 5-carbon RUBP, there are 3 molecules of them, will now react with the Rubisco, or with the use of the Rubisco, an enzyme, and it will be reacting with carbon dioxide, so that each of the RUBP will receive 1 carbon dioxide, so that there will be 3 molecules of a 6-carbon intermediate. So 1, 2, 3, 4, 5, 6. So you will be putting each 1 carbon dioxide to each of the RUBP, and then this will automatically, because it's unstable, cut itself to produce 3 carbon molecules. So since there are 3 copies or 3 molecules of the 6-carbon intermediate, and you cut it in half, you will now have 6 molecules of the 3-carbon molecule, which we call as the 3-phosphoglycerate. And that's the carbon fixation, the first stage of Calvin cycle. Now in the next stage of the Calvin cycle, what happens next would be that the 3-phosphoglycerate, the 3-carbon molecule, with the addition of ATP, so phosphate will be added to that, and you will use 6 ATPs here, will now produce 6 molecules of 1,3-bisphosphoglycerate. Alright, so you have again 3-phosphoglycerate with the addition of 6, or the use of 6 ATP, adding 6 of this phosphate, and then it becomes 6 molecules of 1,3-bisphosphoglycerate. So the phosphate here now is attached to the carbon number 1, becoming 1,3-bisphosphoglycerate. Now what happens next is that the phosphate will later be removed in order to make it a aldehyde. So 6 NADPH will be used so that the hydrogen will now make the first carbonylaldehyde, so it now becomes glyceraldehyde 3-phosphate. So this is the reduction phase. Now do take note that there are 6 molecules of G3P, one of which will be going out of the Calvin cycle, and then it will later be used for the production of glucose and other organic compounds. So this would mean that there is the remainder of 5 molecules of G3P. And the last stage is what we call as the regeneration of RUBP, wherein with the use of 3 ATPs, so the phosphate will be used up, the G3P, the 5 molecules of this will be rearranged to produce your 5 molecule RUBP, or ribulose 1,5-bis phosphate. So there is a rearrangement. So there are 15 carbons here, 15 carbons here. So there is a rearrangement of the G3P carbons to produce 3 molecules of RUBP with the use of 3 ATPs. So that's the whole of the Calvin cycle in summary. So we need to take note of the number of ATPs here, the number of NADPH here, the number of ATPs needed here, and of course don't forget the names: 3-phosphoglycerate, 1,3-bisphosphoglycerate, G3P, glyceraldehyde 3-phosphate, and ribulose 1,5-bisphosphate. So those are the important things that happens or in Calvin cycle. So let's try to remember all of this. So this one is what we call as ribulose 1,5-bisphosphate, and then what is the input? It is carbon dioxide, 3 molecules of this. What's the name of the enzyme? It is Rubisco. So this 5 carbon now becomes a 6 carbon short-lived molecule, which will be cut in half to produce 3-phosphoglycerate. With addition of ATP, 6 of this, it now becomes 1,3-bisphosphoglycerate. With addition of NADPH, 6 of this, it now becomes glyceraldehyde 3-phosphate, one of which will be going out of the cycle to be used for glucose production, 5 of which will be used to produce ribulose 1-bisphosphate, but with the addition or with the use of 3 ATP. Again, this would be carbon fixation phase, reduction phase, and regeneration of carbon dioxide acceptor. So that's the whole thing about the Calvin cycle, so we're able to review. Now there are a number of things that we also need to take note of. It would be how to compute number of ATPs, number of NADPH. So, for example, this question: for every carbon dioxide that enters the cycle, how many ATP and NADPH are needed? Now, going back to our Calvin cycle, you will be noticing that there will be there are 3 carbon dioxide entering into the cycle, which means there will be 3 turns later on. So it will be entering the Calvin cycle, and then for this 3 carbon dioxide, you will use 6 ATP plus 3 ATP here, so a total of 9 ATPs, and then you will use 6 NADPH here. So the ratio would become, for every 3 carbon dioxide, 9 ATP and 6 NADPH will be needed. If you divide it by 3, you will have 1 carbon dioxide, 3 ATP, and 2 NADPH. So this will be the ratio that you have to take note of. So for the question, for every carbon dioxide, you will use in the Calvin cycle 3 ATP and 2 NADPH. These are very important for the computations that we'll be needing for this portion. Now take note also this question: how many ATP and NADPH are used if 4 carbon dioxide molecule enter the Calvin cycle? We already computed how many for 1 carbon dioxide. So in this case, if there's 1 carbon dioxide, again 3 ATP and 2 NADPH. So in this case, you will just have to multiply them by 4. So since the question is 4 carbon dioxide entering into the Calvin cycle, so you multiply by 4. So there's 4 carbon dioxide, 3 times 4 is 12 ATP, 2 times 4 is 8 NADPH. So very easy to compute. Another question: how many ATPs and NADPH are needed to produce 1 glucose molecule? Now do take note that for 1 glucose molecule, there will be 6 carbon that are needed to produce that, which implies 6 carbon dioxide would be needed to enter into the Calvin cycle. So there will be 6 turns of that. So if there will be 6 turns, then there will be 18 ATPs and there will be 12 NADPH. So take note again of this one. So if there will be 1 carbon dioxide, there will be 6 carbon dioxide needed to produce a glucose. So 6 times 3 is 18, 6 times 2 is 12, and that will give us the answer over here, 18 and 12. So don't forget this ratio as well. So as the number of glucose increases, then the number of ATPs and ATPs will also be increasing. This time, 2 glucose molecules were synthesized through the Calvin cycle. So how many ATP and NADPH? You just multiply by 2. We know that's 18 and 12. So it now becomes 2 glucose, 36 ATPs, 18 times 2, and 24 NADPH, 12 times 2. So the more glucose that you will have, you will simply be multiplying that to 18 and also 12 NADPH. So quite easy. How many ATPs and NADPH are needed to convert 6 carbon dioxide molecules to 1,3-bisphosphoglycerate? So in this case, we're not going to finish the whole of the Calvin cycle, but we're just going to go up to the 1,3-bisphosphoglycerate. So take note of this. In this case, you will now have 3 carbon dioxide entering here, so which will be needing 6 ATPs to become 1,3-bisphosphoglycerate. So take note of the ratio. So there were 3 carbon dioxide a while ago, 6 1,3-bisphosphoglycerate, and 6 ATPs needed, as we have seen in the diagram over here. So since the question is there are 6 carbon dioxide molecules, so we just multiply by 2 to become 6 over here, multiply by 2 to become 12. 6 times 2 is 12. So the answer to this is 6 times 2. It now becomes 12 ATP. So for 6 carbon dioxide to become 1,3-bisphosphoglycerate, there is a need for 12 ATPs to be used up. So that's how you will be computing if you're going to take note of the different intermediate molecules inside of the Calvin cycle. Alright, so that's the answer to that. Now, going to the next topic, which would be the alternative pathways. We have here important things. So one thing that we have to take note of is that plant loses water through the stomata, and this is called transpiration. And then this, if there's too much transpiration, therefore the plant will die. So there is a need for the plant to survive, which means the way by which the plants do that would be to close their stomata, as you can see over here. But closing the stomata in order, or the stomates, in order to reduce the loss of water has also problems with that, and that is because since the stomata is closed, carbon dioxide cannot be used, which implies photosynthesis will eventually stop. So that would be one of the problems. So again, dehydration is a problem for plants, and plants will be closing their stomata to minimize water loss. The problem with that is that it reduces access to carbon dioxide but also build up oxygen at the same time. And then what will happen is what we call as photorespiration. So please do take note that Rubisco is an enzyme that has an affinity to both carbon dioxide and also oxygen, but depending on the concentration, it will be binding to either carbon dioxide or to oxygen. So take note, if the carbon dioxide content is higher, then the Rubisco will bind with carbon dioxide, and the process will proceed towards Calvin cycle, which will later produce glucose or other sugars. However, if there will be the absence or the lessening of carbon dioxide, which means the increase in the oxygen, Rubisco will now interact, or Rubisco will now bind with the oxygen, and what will happen is that there will be what we call as photorespiration. So it will proceed towards photorespiration, wherein instead of producing glucose, it will now start breaking down organic molecules like glucose. So take note, when carbon dioxide is high, Calvin cycle happens and photosynthesis increases and glucose production increases. When oxygen is high, then photorespiration will happen and organic molecules will be broken down. All right, so that's why there are other alternative pathways in order to minimize photorespiration. So let's take note of this one. So for the C3 plants, this is the normal Calvin cycle that we have discussed a few moments ago. So simply the carbon dioxide will enter into the Calvin cycle, and then the reason it's called C3 because it becomes a 3 carbon molecule, which is shown as 3-phosphoglycerate over here. So that's the one of the most important distinguishing feature of the C3 pathway. Now also take note that because if carbon dioxide is less, then it will undergo photorespiration, and that's a problem with C3 plants. But however, if there is an increase in the carbon dioxide, then there will be no problem. No photorespiration happens, but rather more photosynthesis, more glucose will be produced. However, in very hot climates where the stomata will be closing, then we could expect the carbon dioxide to lessen and photorespiration to happen. So these are the other alternative pathways, which we call that the C4 plant. And for the C4 plant, as you can see in the word, the carbon dioxide is fixed into a 4-carbon molecule. And this is it. It's called oxaloacetate. So from phosphoenol pyruvate, it will now become an oxaloacetate 4-carbon molecule once the carbon dioxide will bind with the PEP. So that's the distinguishing feature of the C4 pathway. Okay. Now, in addition to that, there is also the separation of space because unlike the C3 plants, which happens inside of the mesophyll cell, the fixation of carbon dioxide into a 4-carbon molecule happens in a mesophyll cell, and then the C4 or the carbon 4, the 4-carbon molecule will then release the carbon dioxide into what we call as a bundle sheath, which will enter the Calvin cycle to produce later glucose. So you can see in the C4 pathway a separation of space, mesophyll cell, and also bundle sheath. So let's look at some of the characteristics. So again, C4 plants, carbon dioxide is fixed into a 4-carbon compound, and there are two distinct type of cells, the bundle sheath and also the mesophyll cell. So the most important thing that is happening here is that by the use of the mesophyll cell, it will able to what we call as concentrate carbon dioxide into the bundle sheath, so thereby preventing oxygen to come close to the bundle sheath, and then prevents photorespiration to happen. We'll show that a little bit while as we show the bundle sheath. Other things we have to take note of is that the PEP carboxylase in the mesophyll cell is the one that will be catalyzing the 4-carbon precursor, and then these 4-carbon compounds are exported to the bundle sheath. So this will later release the carbon dioxide. So again, this is the C3 plant, and this is the C4 plant. We can see clearly the difference. The mesophyll cell are surrounding the vascular bundle. So the mesophyll cell, this is where the C4, the fixation of carbon dioxide will happen. Once it is inside of a C4 molecule, it will now be transferred towards the bundle sheath here, and then it will release the carbon dioxide. So you will see, since the mesophyll cell would be surrounding the bundle sheath, it will be concentrating the carbon dioxide into the bundle sheath, thereby preventing oxygen concentration to increase. So this is the adaptation of C4 plant. By increasing the carbon dioxide, it will be preventing photorespiration to happen, and then it will allow the Calvin cycle to happen here. Now, you will see here again the separation of space. How about the last one, which is the CAM plants? And the word CAM will be coming from the crassulacean acid plants. So this is almost the same as the C4 plants. So the carbon dioxide is also fixed into a 4-carbon molecule, as you will be seeing here. So it's the same phosphoenol pyruvate, a 3-carbon, will now be fixed with carbon dioxide becoming oxaloacetate or 4-carbon molecule. But the difference would be between the C4 and the CAM plant is that for the C4 plant, it's fixed in the mesophyll. For the CAM plants, it's fixed also in the mesophyll cell, but there is now a separation of time. So the fixation of carbon dioxide into C4 happens at night time, and then the C4 will simply be accumulated inside of the vacuole, and then later at daytime the carbon dioxide will be released into the Calvin cycle. So this is a separation of time, this is a separation of space. So what happens here? So take note that mesophyll cell will now, carbon dioxide will enter, and then it will become a 4-carbon molecule, change into malate, and then becomes pyruvate later on, releasing the carbon dioxide into the Calvin cycle. So this is how the strategy in order to increase the concentration of carbon dioxide to prevent photorespiration to happen. Now, other important things is that the stomata closes during the day. That is where this portion will happen, release of carbon dioxide and carbon dioxide. And when at night time, where there is no transpiration that could happen, less loss of water, this is where carbon dioxide can be fixed to become a 4-carbon molecule. So very interesting. So here it is. So the carbon dioxide is fixed to a 4-carbon oxaloacetate, and then it will be stored inside of the vacuole at night time, where the stomata is still open to allow carbon dioxide. Once it's daytime, the stomata will close, but no problem, because the 4-carbon molecule will release the carbon dioxide